Welcome to Mastering Solutions. We aren't asked to draw a ray diagram with this, so we're only going to do the math for these ones. So we need to find the image position and the height. So the image position is going to be S prime, and the height of the image, of course, is H prime. We'll start with the image distance, and we're going to use the thin lens equation to solve for that. So we know that the thin lens equation says that the power of the lens is equal to the inverse of the focal length in meters. That's equal to 1 over S prime plus 1 over S. We need to solve for this, so if we minus over 1 over S, we have 1 over S prime, or the image distance, is equal to 1 over F minus 1 over the object distance. 1 over S prime is equal to the focal length, which in this case we have a converging lens, so the power will be positive for a converging lens, negative for a diverging lens, and the focal length is 30 centimeters, which obviously is 0.3 meters. We're going to minus the object distance, which we're told is 10 centimeters in front of a converging lens. So this is inside the focal length, meaning it's closer to the lens than the focal length is. So this is going to give us a negative value for the image distance, meaning that it's a virtual image. So these are really important to remember, the sign conventions. So we have 0.1 meters. This, since the object is on the upstream side of the lens, meaning it's on, if we were to draw it, it would be on the left side of the lens. If this is the lens, and the image will be over here on the same side as the object. We've done a lot of those in the past few questions, so hopefully that made sense what I just said. Putting this in, we have 1 divided by 0.3 minus 1 divided by 0.1. And so we have negative 6.67. And that is diopters. We don't want diopters, obviously, we want meters. So if we take the inverse of that, that gives us negative 0.15 meters. So the image distance is a negative 15 centimeters. Since it's negative, like we just talked about, that means it's on the same side as the object, and it's a virtual image, so it would be upright. Now we need to calculate the height of the image. And we can use the relationship of H prime over H is equal to a negative S prime over S. And that's obviously from the magnification equation. And so we're just going to take this section and set these equal to each other. We want to solve for this though. So if we multiply both sides by H, now we have the image height is equal to H times the negative image distance over the object distance. So H prime is equal to the height of the object in meters, we said is 1 centimeter, so 1 times 10 to the negative 2 meters. Now we have negative, the image distance is 0.15 meters divided by, and that is negative. This negative is from the equation, this one is from the answer, so don't forget those, that is important. And then the object distance, S, is 10 centimeters in front of the converging lens, so that's a positive 0.1 meters. So we have 1 times 10 to the negative 2, not negative 3, and then we're multiplying that by a negative times a negative, I'll put it in. It's a positive 0.15 because the two negatives cancel each other out, right? Negative, and then negative 0.15. And then that's divided by the object distance, which we said was 0.1, positive 0.1. There we are. All right, so we have, this is a meter, so 1, 2. So that gives us 1.5 centimeters, and that was a positive 0.15. So what that means, the positive indicates, because the sign convention, that we will have a upright image, which agrees with this where we said it's going to be a virtual image, meaning the distance is virtual and the height is upright. So it's a virtual and a upright image. So these are the answers, the 15 centimeters in front of the lens on the same side of the object, and it's 1.5 centimeters tall. So we have a little bit of magnification there.